When I think about mathematics, I always picture it as this bottom-up process. You start with these solid foundations, the axioms, and you build up from there, like constructing a skyscraper.
That's the classical view, absolutely.
Yeah.
But what if you flip that whole process around?
Flipping it, how would that even work?
Well, that's the core idea behind a really fascinating field called reverse mathematics, or RM. It was largely developed by Harvey Friedman and Steve Simpson.
Okay, so reverse mathematics. I'm intrigued.
Instead of asking what we can prove from a set of axioms, it asks for a given theorem, what are the absolute minimum axioms we needed to prove it in the first place?
And you're going backwards. You're starting with the theorem and asking, what was the foundational cost of this truth?
Exactly. And to do that, you can't just use standard set theory. It's, frankly, too powerful. It would prove everything at once. You need a more controlled environment.
A kind of mathematical laboratory.
Precisely. And that setting is usually a system called second-order arithmetic, or SOA.
And why SOA? What makes it the right tool for the job?
Because it's expressive enough to talk about most of undergraduate math. We can represent things like real numbers and functions as sets of natural numbers. It gives us a framework to measure the complexity of these theorems very precisely.
Okay, so you've got your controlled environment. But to measure anything, you need a starting point, right? A baseline.
Right. And that's the base system, which is usually a very weak set of axioms called RCA 0. Think of it as the bare minimum. It's strong enough to state a lot of theorems, but it's actually too weak to prove most of them.
So that's the key. You have a theorem you know is true, but your base system can't prove it. So how does the reversal part actually work then?
It's a really elegant two-step process. First, you do the normal thing. You take a stronger axiom system, let's call it S, and you prove your theorem, T. That's step one.
Okay, that's the standard forward direction.
But then comes the magic, the reversal. You go back into that weak base system, RCA 0, and you prove that the theorem T itself implies the axiom system S.
Wait, the theorem implies the axiom.
Yes. It shows their equivalent in logical strength. The theorem is not just a consequence of the axiom. The theorem is the axiom in disguise.
That is a profound idea. So you're not just proving things, you're classifying them.
We are. And this has led to this incredible hierarchy. Most of classical mathematics falls into one of what we call the big five subsystems of SOA, all ordered by strength.
The big five. Okay, let's touch on a couple of those.
So the base is RCA 0, which we mentioned. It roughly corresponds to computable mathematics, things you could, in principle, run on a computer.
And what's an example of something that fits in there?
Get this, the intermediate value theorem from calculus.
No way. Really, that feels way more powerful. So you're saying it doesn't require any non-computable ideas?
Not at all. But then you take one step up to the next system, WKL0, or weak Koenig's lemma.
And this is where things get more complex.
This is where a certain kind of non-computability enters the picture. And what's wild is that so many famous theorems from analysis are equivalent to WKL0. For instance, the Heine-Borel theorem.
The Heine-Borel theorem is WKL0.
Over the base system, yes. The logical strength required to prove it is exactly the strength of that axiom. Then you go even higher to ACA0 for things like proving that every countable vector space has a basis. You're putting a precise price on each theorem.
It's all about understanding the resources you need for the job.
That's the perfect way to phrase it. It's about foundational efficiency.
And speaking of understanding foundational challenges, this deep dive is sponsored by Embersilk. Just as reverse mathematics pinpoints the necessary logical strength for a proof, Embersilk can help your business find where AI agents can make the most impact, from training and automation to software development. You can find the right tools for your digital strategy at embersilk.com.
Ultimately, what reverse mathematics gives us is this beautifully structured map of mathematical truth. It connects the complexity of our axioms directly to the complexity, the computability or non-computability of the universe they describe.
It's just so inspiring. We have this tool that can measure the exact logical price of a theorem. And if we can bring that kind of rigor to understanding the foundations of math, it just opens up so much clarity for future discoveries. I mean, imagine what that could mean for guiding AI and developing new proofs. It's incredibly hopeful. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.